So really briefly, I'm not even yellow yet. Okay, I'll tell you a bit about what we've done in our lab, just as an example of one set of projects that has engaged students at a variety of levels in our department and other people outside. So for about 17 years now, thank you, Catherine, for the introduction, I've been working on microfluidic stuff, and I apologize if I've led people down a messy path with leaky devices. But they've ranged from things made in silicon and glass to lots of plastic parts. We started a spin-off company called Micronics. A statement here is I have stock options in Micronics, so you can assume that I'm lying most of the time, I guess. And they said, oh, silicon's too expensive, let's go with plastic and glass, because they wanted to do disposables, or plastics. So we've done a lot of stuff in plastics with them and by ourselves in a variety of contexts. It's a cheaper way to go. We typically use a CO2 laser cutter, which is cheaper than a silicon fab lab, but still about $20,000 to buy one of these things. What you do is you cut out bits of plastic and then you stack them up one on top of the other, and you basically alternate double sticky Scotch tape with various bits of plastic, and instead of having circuitry for electrons, you have circuitry for liquids, so you can push things around and you can make fairly complicated structures out of these things that do a variety of parts. You did hear correctly that often there is, however, a refrigerator full of stuff around it, which is part of the original problem of this technology. But you can make things like, well, that's the guts of a flow cytometer. You still need light sources and pumps and things like that to make it work, but you can make disposables in ways you couldn't otherwise do. And back in 2005, we responded to the Gates Foundation's request for proposals for what was called the Grand Challenges in Global Health Program. It still exists. It officially ended for our funding on end of July, but we're still in sort of a no-cost extension until the big meeting here in Seattle. Grand Challenge 14 was technologies that assess individuals for multiple conditions or pathogens at the point of care. And I'm going to really briefly summarize 5 years and $15.4 million. I've got a couple of students in here who are chuckling because they've been through the pain for the last 5 years. It's been a team project. Our group basically, I was the PI, we sort of did immunoassay reduction to microfluidic format in my group. Pat Staten in our department did my molecular systems development. What was originally Epoch Biosciences then became Nanogen. Nanogen went bankrupt. The piece that we were dealing with went back and became the Elitech group as Nanogen. So and all this happens while you're trying to keep the team together. It's very exciting, trying to keep companies on the same track. Micronics was heavily involved as sort of the systems integrator and working on the nucleic acid side development. They subbed to an Australian company to work on the instrument development. And heavily involved was also Path. Path got involved in choosing which particular analytes we wanted to go after, vetting a variety of reagents, doing what's called the user needs assessment, which is really a very critical element to make sure there is someone at the other end who cares what you're doing and helps you design it. And a lot of work of that sort, and sample procurement. What we were designing was a platform, okay? And that means a system that will work for a variety of applications, of a variety of diseases. For rapid differential diagnosis of disease states, we wanted to be able to do 6 pathogens, because the idea was someone would come in with a syndrome and you say, okay, what of the 6 most likely causes that could exist in this particular part of the world could be actually causing their symptoms right now? PCR was one of the things we wanted to put in the device. We also wanted to do immunoassays for either antigens and antibodies, so we could do serology tests or actually look for specific antigens. We aimed for a turnaround time originally 15 minutes. By the time we were done, we were sort of changing all the slides and saying 30 minutes, because that's what we thought we could do per sample. So one sample in, 30 minutes of running, next sample can go in the device. We wanted a disposable that contained all the reagents, meaning one simple thing that had all the reagents and the instrument would stay dry. You'd put your sample in, push, run, and walk away. And then when you're done, all the biological waste would stay on that device as well. We needed on-card calibration and test validation. It had to be small, lightweight, rugged, battery-powered, because we wanted to be able to backpack this into a small village someplace, or recharge it from your Land Rover, but not require mains power at all any place. It needed to be simple because we wanted this to be used by healthcare workers in the periphery, not by someone with a PhD. And finally, I think the last bullet, low maintenance, and then the very last one after that should be low cost. Sorry, it almost disappears off the bottom. Low cost for box and disposables. That's, of course, the hard one. Okay, I think I'm 7 seconds over. I'll go quick. We did say we had a little extra time, right? Okay, good. These are the pathogen list. I don't want to go through it. It's a variety of things that produce rapid onset fever. That was we're trying to differentiate. And I really won't go through it except to say blood into the card, then everything else, once you've inserted the card in the reader, everything else happens inside. What I'll point out is in my lab, we spent a lot of time looking at dark spots on a white piece of nitrocellulose. So we got very, very good at quantifying how much analyte was there by looking at how dark a spot got. Please. Here, okay. And basically that's what the insides of the thing look like. There's a computer in here, lots of valves, lots of 2 pressure sources and a vacuum source, lots of little Lee valves, and there's a card to show you how big it was. If this were to work, this woman would now start actually running the card. This is something that I spent a lot of time yesterday with the AV people making work, and obviously it's not going to work. But basically this thing is about that big. The card is about the size of a big cell phone and fits in there. The project had a lot of people working on it. This is just a small list of the people that worked in my lab. It was over 100 people easily working on the project over the 5-year period. What happened at the end of the project is now Micronics is responsible for commercializing what we call the DX box or Diagnostics box. It's entirely up to them. That's a really interesting aspect. Things changed a lot in the course of Gates' funding of this thing, and we could have a very long discussion over lots of beer about whether the perfect way to get across that aforementioned valley of death. It's an interesting problem for a technology, and this one's pretty far down the road. It actually works. Now, last point is what we're calling microfluidics 2.0 or 2DPNs, and I'll explain what those are. So the problem is microfluidics inexpensive enough for the endpoint? And I'll say, if any of you have seen George Whiteside's TED Talk, you'll get a good hint of where I'm going with this. The problem is, if you look at the guts of our microfluidic device, we had 23 layers of plastic plus things that we had to pick and place in there. And the thought of converting that to a low-cost disposable woke me up at nights for about 4 years of the 5. It's just a really scary prospect when you realize you're not really going to make it in terms of final low cost. Sorry about this. The answer, of course, is something like lateral flow, which is actually very good and very cheap for what it does. It has some limitations, like, well, they're, one large sheet cut into strips. They're all linear, so all the fluid movement is in one direction, and they give you a limited set of chemical reactions carried out in sequence, which limits both the sensitivity and the complexity of what those things can do. They're very simple. And as long as you're willing to go with simple, you can get the cost way down. So what if you eliminated the 1D limitation, the idea of going in a straight line for lateral flow devices, and instead went to 2 dimensions? Then you can perform, we think, arbitrarily complex chemical processes by sequencing flows. You can use capillarity, the actual sucking of the liquid across the porous nitrocellulose or other materials, instead of all the pumps. So we can now throw away most of the DX box and basically have multiple legs to start and stop flows. We argue that you can do most of the conventional chemical and biochemical processes, and I mean most of the processes, not just the ones in analytical stuff, but with channel-based microfluid processes that you could do, but simpler. And if you, we think there are lots of PhDs in this, but the cost for making these things for global health can really be absurdly low, and that was where we got very excited. So we think of it really as paper dolls, cutting out bits of paper into particular shapes, and each one of these becomes a chemical processing unit that we will design. So general idea really is this. There's a piece of paper. Up here we have a bunch of capture zones with different spots that are kind of small. You put your reagents on different legs, and then you put your sample, whether it's a drop of blood, sputum, urine, over here, and then you basically put water underneath it, and the water moves up by capillarity. And because these things are different lengths, things arrive over here at different times. And that's the basic idea of what we're trying to do. You bring different reagents from different times to do sequential processing. We need a housing for this, again, and again, this is a model, but it's basically 2 pieces of injection molded plastic, one of which has a trough, a hole for putting the sample in, and here a lens. And why a lens? Because we all carry the instruments on our wallet these days. And these things, as you know, have gotten ridiculously close to ubiquitous in the developing world. We say, let's use this particular piece of hardware, particularly with a camera, as the hardware for doing the analysis. Put it together, and you've got a 2-dimensional paper network diagnostic device that should be really cheap. So the aim is use the cell phone, the available already relatively low-cost analysis instrument to either run the code over here and do the analysis of spots, or send the image to someone else who does the analysis for you. So it can actually be a relatively cheap camera phone. And then you bring in all the rest of this. We tested this out back in 2008. Barry Lutz did this in his kitchen. So please note the high-tech stuff. This T sensor, which is what we developed about 15 years ago with the guy who's now actually running past Diagnostic Group, fabricated with scissors and fingers, no material cost of a few cents. The point is, from 15 years ago, when Bernhard Weigel first invented this thing, we've cut the cost 35,000 times. Then we said, this is going to work. So since then, we've been running as fast as we can, doing this. We got funded by one of those ARRA challenge grants from NIH, so we had 2 years of funding to see if we could take this to essentially a 2-target measles dengue test from 2 drops of blood with onboard sample prep, size of a credit card, less weight. That should be a milligrams, not 100 grams there, by the way. So we're going after this. We've done experiments and models and showed that we actually understand the flows in the paper quite well, and we can get quantitative agreement between computer models of this thing. We really do some engineering in all this. This is an example of how you can take 3 solutions, and then by having them connected to a single common one, you can have a single place over here that first gets solution 1, then solution 2, then solution 3. That's why I wanted the lights low. Sorry about that. This is actually a system where we're doing this with an amplification reaction to get more sensitive detection for an immunoassay. So we're actually demonstrating that this spot, which is much darker than that spot, actually gives us amplification. Bottom line is the general approach is working. 1 year into it, we've published 4 or 5 papers. Dean Stevens, who's over there, finished up his thesis, and his work over here was converting spot densities and looking at these capture for an immunoassay and then an amplification process with a gold enhancement probe. All this is actually analyzed from pictures from movies he made with his iPhone. So he's making movies with his iPhone and getting kinetic data, and the most recent numbers show 4 orders of magnitude dynamic range for some of these assays, all done with an iPhone. So we're kind of excited about that, and it's moving in the right directions. If you want to make these things, there's something called a Cricut, which actually allows to cut out paper, and it will also cut nitrocellulose very effectively, it turns out, including back nitrocellulose. So this thing costs about $179 retail. To print reagents, we're actually printing things with a slightly juried Epson printer. The printer is normal. We've gotten into the cartridge with a saw and put in pipette tips. So now we can print things. So with a total investment of $300 and a garage and a laptop, you can now start creating point-of-care diagnostics in your garage. All you'll need is maybe 1 penny a shot for the disposable housing and water. So as the final thing, so we're going, I think, from what's on the market today, call it the Cephia Gene Expert and lateral flow stuff. The DX box is in development and should be on the market within 2 years for certain. And then where we want to go in the next few years is this cell phone-based stuff where the disposable really can be down below $1, and then all you need is the buck and water and a sample and you're off and running. Lots of people involved in the team. Again, lots of them, please notice, graduate students and undergraduates in this ongoing project right now. So I'll leave it at there. Thank you.